Stephen Round, and we're here to learn about LOPA today from Mr. Pinkney.
Thank you. Hi there. Okay, so again, I'll just, I think I've met quite a few of you before. I'll just start with a quick introduction of myself. So my name is Ian Pinkney. I've basically been on the scene in the instrument world for over 40 years now. So started at 16 at ICI as time-served apprentice, then did my degree there, and then I went on to Spectratech, which was at the time was famous for flow metering. After that, I followed with Amoco and BP, which I was there for 20 years. But it was in that time that I sort of specialised. I haven't specialised in a few other areas. I specialised eventually in safety systems and functional safety. So as an FSA assessor, I was one of the first in BP to set up our functional safety assessment programme up, because we didn't even start until about 2007, and initially it was for the subsea world. So I worked with a couple of people called Mervyn Curry and Bill Black, and Bill Black was actually on the IEC 61508 committee and 61511. He was a great person to work with, and I don't know if he's still about, but oops, sorry. Anyway, since that time, I've continued developing my functional safety assessment methodology, the way I do things. I've got quite a successful process, which has now become quite highly regarded by many companies, and I've also have a minor FSA 5 process for dealing with everything from a simple set point change to say modify 1 or 2 SIFs. So that's my background, and I'm going to do this. I want to do this presentation on LOPA, but I wanted to also take an opportunity to dedicate this to Dan Haddon. Now, some of you, he came here regularly to these meetings. Unfortunately, he's gone now, but a young engineer. Young as my eyes anyway, a good and a dedicated engineer, husband and dad, and I'm just going to be missed by all his colleagues and people who knew him. Okay, so functional safety assessment. Right, so the basis of these, it shouldn't happen to a functional safety assessor presentations. The idea is for me to basically let you know what sort of common failures we identify, so that you can learn from them and see if you can improve the way you do things yourself to avoid these findings. So that's what the aims are, and today we're going to be doing this. But firstly, I have this standard statement I always make about BS 61511 or IEC 61511. It's basically worth saying that this standard was developed by a team of humans, and as such, it was done with varied outlooks from the international people, with individual biases and personalities, varied competencies, national and company and individual objectives in mind, with varied opinions and tolerances, and using different vocabulary and terminology. And when you read 61511, you can see a lot of this in it. So there's a lot of inconsistencies, compromises, discrepancies due to all these factors. But in my opinion, it's not perfect, but it's not far off. It's very, very good standard. Now, I like to also talk about language. And in this particular area we're talking about, there's, we're going to be talking about, I like to look at the sort of terminology we use. So different companies, sectors, businesses, etc., they use different terminologies for exactly the same thing. And these have evolved often from the common ancestry. And then have developed specifically for their areas. Now in phase 2, there are many terms and associated techniques used to carry out the allocation of safety functions to protection layers. That's the official title it's given in the standard. It's a mouthful, and I tend to use risk allocation as my standard term, or meaning what phase 2 is about of the life cycle. And there's different methods to do it. Now, we have the calibrated risk graphs was a method we used a lot. It was a very simple method. It's rarely used these days, but it was used a lot back in the early days. There's semi-quantitative methods, layer protection analysis, LOPA, which is a rules-based method. It's basically a fault tree underneath, but it's what we're doing is, instead of looking at the fault tree side of it, we've got the fault tree is the logic part of it, and we're setting ourselves rules of and a method to how we fill it in. But with them rules becomes basically requirements that must not be broken. Fault tree analysis by itself is used as a semi-qualitative analysis is more flexible, and it's worth looking at times as for that flexibility. If you have a high complex or scenarios with lots of fatalities, then a QRA with a fault tree is often the best approach, and avoid using LOPA. I noticed some companies use LOPA for high demand, situations. Again, that's something I would use fault tree for. LOPA, again, it struggles, and then there's the maths which I won't go into, but that would show how why it sort of breaks down for things like high demand. A little bit of history. In the early days, and I still come across it, the LOPA was often called SIL determination. That was the term, and the reason it was called SIL determination, it goes back a little bit in history. When IEC 61508 was initially came out back in the beginning of this century, the process safety or process engineering at the time often stopped at HAZOP. They did the HAZOP, and there wasn't anything really that followed, and there was a gap that between the HAZOP and the need for us to find a SIL level for which we need to grade our safety systems. And initially we used the risk graph method. That was the early days, back 2004 and so on. And then later it became LOPA was the method, but it was often the instrument guys that would chair LOPAs. So you still get a lot of experienced instrument guys still chairing LOPAs, but but it's now become more of the process safety have taken over that sort of chairing. They've become much more into that now. And for this reason, that the younger instrument engineers don't have the same exposure to LOPA that we used to have, back only 10, 15 years ago. And so when I did this presentation, there was part of me wasn't going to say, oh, this is what LOPA is and this is how it works, because I thought you'd all know it, but I thought, well, maybe you don't, because some of you are quite young and you may not have had that experience. So I thought we would cover some of the basic principles of LOPA first. So Before you can carry out a LOPA, you've firstly got to identify the hazards. That's phase one of your safety life cycle. So you go through your HAZOP. HAZOP is probably the most common method. There's other ways that you can identify hazards, but the vast majority of your hazard scenarios are identified using the HAZOP process. So you go through your HAZOP, you identify your nodes, you look through your nodes, and you use keywords to identify initiating causes. And then for each initiating cause, you say, could this end up with a hazard? And if it does, what would be the consequence of that hazard? And therefore, if there's a big consequence, what would be the overall risk? So the risk mitigation you're looking at there is without any safety systems in place. You're just looking, if this happens, there was no safety systems in place, no mitigation, what would be the consequences? What would be and therefore you give a risk. So you end up with if you imagine each of these arrows are the hazard scenarios, and you end up with ones which are obviously higher and in the unacceptable region, and others that are tolerable if a LARP, or even maybe some ones which are straight in the acceptable region. The ones which are in the unacceptable region, they're the ones that need to go through into your LOPA, because there you need to do more analysis. And this is where the purpose of LOPA is to identify independent layers of protection to reduce that risk, basically by risk reduction factors, you could say, reduce that risk down and get below into the tolerable if a LARP region. Once it's in there, basically the LOPA really comes to an end, but that doesn't mean it's the end for that particular risk. You still do a LARP demonstration to look at, is there more we can do? Can we lower that risk more further? Or is it going to be grossly disproportional in time or effort and costs to bring it down further? So I'm going to talk about the method of the LOPA. But before we do so, I just want to touch on TMEL, Target Mitigated Event Likelihood. I've sort of didn't know where to sort of place this. Originally I placed this after the method, and I thought, well, it doesn't make sense there, so I thought we'd talk about it first. So going back to this diagram, the target mitigated event likelihood is basically that target line that's between the unacceptable region and the tolerable if a LARP region. It's a frequency. It's a frequency value of what is acceptable for that particular type of risk, and that's what we're trying to achieve. Often it's just another way of describe it is the scenario risk target. Okay. Now, the scenario risk target isn't a fixed target. It depends on the size of the risk and the severity of impact. So it will change. If it's going to involve fatalities, it's going to be a much more demanding and lower frequency to achieve than if it's for injury, which will be relatively a higher frequency that would be acceptable. Now, you'll notice on my chart here that I haven't put any. I haven't put any values in this, to 10 to the minus 6 or whatever. And we could argue, because I could spend the rest of the evening arguing about what these values should be, because in the UK process safety sector, there is no single legal mandated or industrial accepted set of TMEL targets. The companies need to define their own risk profile and demonstrate it meets the legal requirements under the Health and Safety at Work Act. However, the company must also account for both individual and societal risk and demonstrate that the risk is both tolerable and allowable. Now, so what you end up with is you end up with three targets: one for scenarios, one for individual risk, one for and one for social risks. They're all obviously related because they're all related by risk. But sometimes you can't. If you try to bring them together, it becomes really murky and muddy waters. So you have to have a method of dealing with all of these three. Or we don't have to. Of course, the safety have to have a method of dealing with these individual risk targets and bringing them and demonstrating them, bringing them together. So as a result, there's little no consistency between companies that I've seen across the UK, and the choices made are often not adequately justified. So you can have different targets. That's fine, and it's just that they need to be justified. They need to be how them targets stand up needs to be fully explained. The reason is because if you don't write down the explanation, the HSEs will soon question you on it. That is guaranteed. So though it's not a requirement of 61511, the UK FSA Assessor for common facilities should confirm at least that there's sufficient evidence that the company has the following three items: a practice that defines tolerable risk levels, the TMEL values, for the different levels of safety and environment, and they are consequence applicable. They should have determined a maximum level of risk to an individual and society, and has a method of determining this risk and an action plan to removing any of these risks, any gaps, and has demonstrated that all the risks are allowed. So they're the key three elements that I tend to look for, even as it's not 61511, and I very rarely, when I do my FSAs, very rarely go away from the normative requirements of 61511, but this is something that I will look for. Now, okay, so let's dive in. I am tempted to go in a little bit deeper here and explain a little bit more, but I just don't. I think it wouldn't work. We could use a lot of time. Okay, let's go into the methodology of how a LOPA works. So, as I mentioned, the first thing you start off with, phase one, is your PHR, your process hazard and risk assessment, your HAZOP, for example, which you've defined your hazard scenario and the initiating causes that result in that scenario. They come from your HAZOP, and there should be a clean link between your HAZOP and your LOPA. You should be able to, a traceable link. Ideally, if you, I like it when I see a HAZOP ID number for all of these initiating causes. And if the ID number's there, and you can put the same ID number on the LOPA, it makes my job as an FSA assessor much more easier, because I can see that traceability. I can see that comes from the HAZOP there. If there's not got an ID number, it may be something that is an initiating cause that the LOPA team themselves have identified that isn't in the HAZOP. And in which case, they need to have an action to say, okay, let's align the HAZOP to include that new initiating cause. So it's so often, one of the things I often find is LOPAs forget about that. They use the HAZOP to identify what they need to do LOPA, but then they just start with a clean sheet and they forget all the work that the HAZOP has done, and there isn't that traceability. So that's something that I will look for. So once we've got initiating causes associated with a specific hazard scenario, The next step is we assign a frequency. We provide a credible frequency to each initiating cause, and we justify it. And one of the things that we'll talk when I get into FSA findings is justification. These are the things that it's the wording is always well, not always missing. The wording is often kept brief because in a LOPA, time is precious. It's costing a lot of money to have a lot of people in a room with plus the chairperson's costs, and you want to get through as quick as possible. And sometimes you don't, not enough is documented, and yet there's so much needs to be justified. So so you need to define a frequency for each of the initiating cause, and you need to justify how you came up with that frequency. The next step is to assign independent protection layers. And I've underlined independent. We talked about LOPA as a rules, is all about rules, and that is one of the rules. They've got to be independent. So we identify various different layers of protection. Some people include the SIF in the layers of protection. Some people don't. Now, if you do include the SIF in the protection layer as a protection layer, that's fine. In fact, it's quite good practice. But what you've got to do in the next step, which is you've got a probability of failure of demand of them layers of protection. You've got to set the SIF to 1, so it doesn't have any impact on the result. At this stage, so we now so this next step is we've determined what the probability of failure is for each IPL, each independent protection layer. So a typical BPCS, we would take it would fail 1 in 10 years, once in 10 years. BPCS is control system, by the way, and that works out as 0.1 times per year. Everything's done as per year. So the frequency is done as per year. The probability of failure demand is done per year. And next step is to include any conditional modifiers, and we'll talk about conditional modifiers in a bit. But I like to think of them as lucky factors, and these are basically if the hazard scenario is that there's going to be there's an explosion in the pump house and one person could be killed, you've got to say, well, how often is one person available in that, is in that building to be killed? So that would be a conditional modifier. If he's only there 10% of the time, that's a conditional modifier you can take credit for, and that's a probability. And as I mentioned, that would be 0.1. So you put a probability factor in for these conditional modifiers. And there's lots of other conditional modifiers, and we'll touch on that again. Eventually, you do a very, very simple calculation. You just times the frequency with your IPLs values, your probabilities, and your conditional modifiers, and you come out with a new frequency value, which is basically your intermediate event likelihood for each cause, your IEL. That's for each cause, and then depending on how many causes you've got, you add them up to get an intermediate event likelihood total. So the math in a LOPA is really, really easy. Then now that is your immediate event likelihood, which is is the frequency of the hazard event occurring after accounting for all the independent protection layers and conditional modifiers, but not the SIS. Remember I said about setting the SIS the SIF to a 1 because you don't want it at this stage. So it doesn't include the SIS. So now you say, okay, let's compare what we've got with our target. which is the final stage. And so we divide our TMEL value. So TMEL of 1e to the minus 4, that's 1 in 10,000 years, a frequency of once in 10,000 years, divided by the calculation, the intermediate event likelihood. And in this case, so it's just, my toolbar's in the way. But in this case, it works out as 0.09, which is a SIL1 gap. And so now, so basically what that's saying is, if you now introduce a SIF as another independent protection layer with a probability of failure of 0.09, your frequency will now achieve the target. Okay, it will just achieve it, but at least you got there. So that's the methodology. Does that so far does that make sense to everyone? Yeah. I should have asked. I should have had who's been involved or a LOPA. Has everyone been involved in LOPAs? Okay. Okay. So that was of benefit. Those people that would have been of benefit for. So that's good. Okay. So now we'll move on to the FSA findings. So in the next few slides, we're going to talk about what's typically, what are the challenges and the things I normally identify in LOPA. What do I expect almost to find? Because they're quite common. Firstly, let me say that it's not just when I'm looking at the LOPA and the issues, they're not just related to this phase 2, but they'll be related to other activities, because like everything in the life cycle, things are linked in to each other. So, one of the questions I'm going to be looking at, if you take the top layer, is the team competent to do the job? Is the FSA is the LOPA facilitator competent? Is the output, the information, is it well documented? Does the report, now it's a key critical document for the site. Is that got proper document number? Is there proper revision control? All these, these factors come in. The LOPA will have generated actions. Are these actions being managed properly? So these are all going to fall out in the FSA. Again, we're going to talk. We would look at that flow of information from the HAZOP, the PHRR phase 1, and through to the risk allocation, and also back again. This thing of, we found something else, and how we go back and align it with the HAZOP. And then the outputs. Where do the outputs go? Well, the outputs go into a common cause failure analysis, and we'll talk about that in a minute, because many people don't do it, and that's almost like 90% of people don't do common cause failure analysis in phase 2. The outputs go into obviously the safety requirement specification, which we've talked about before, and that then is then verified in your SIL reliability calculations. And then during operations, you are doing demand monitoring. Now, demand monitoring is basically, when you do your LOPA, certainly for your first time, it's all based on them frequency determinations you give to the initiating causes, and they're all based on assumptions you've made. So, the demand monitoring is saying, were them assumptions correct? So you should be looking at demands during operations and analysing them, counting them, checking that it's what you've assumed in the LOPA is correct. When you do your LOPA validation about every 5 years, you should be using that data. That data should be available to use and to fine-tune your frequency, initiating cause frequencies particularly. Okay, so the next few things are a bit not as fancy. They're just going to be a load of tables, and I'm just going to discuss some of the typical findings. With information management, so often it's surprisingly how common it is to find that people get the LOPA report from the consultant company, whether it be TUV Rhineland or Exceeder, and it comes with that company's document number, that company's own revision control, and they don't add their own. They don't add their own company's. They don't so say, oh, actually, we need to control this document. They just take it as it is and they file it away. This is again, and I notice more HSE are pulling people up more on this now. They're saying that there are a core set of health and safety management documents that you need to define them yourself, and then you've got to demonstrate that you are controlling them. And often when people define what them are, they will nearly always include, in fact I've not come across a case where they haven't included LOPA reports as a core document. There's other things like on information management that is so common as well. It's I put stars next to some because I just wanted to focus on a few, but I mentioned the traceability between the HAZOP. There's so many things, but we'll move on. Competency. There's not a case where I've come along and said, well, the facilitator wasn't competent to do the LOPA, okay? But nearly every case I come across, there's no evidence of it. So what's actually happened is there's been a good selection process, which is hidden from the LOPA report as such, where they've gone and said, we want a competent LOPA, and they've asked around and they've found, oh yeah, we had with other companies or the other facilities within their company, and they've said, oh, this is a good facilitator, we did a good job here. And word gets around and people tend to pick good facilitators. But the report, I think every report, and it's something I always try and go hit back on a little bit too, not as a non-conformance, but just as an enhancement, is to try and get through to the consultancy groups, is put a statement in there, put something about competency, about yourselves, what you're bringing. How have you, as a facilitator, what competency do you have? How has that been assessed? And what, so usually, does your company have a management process that you can refer to on competency? And the similar is with the facility itself. I find you don't go to a coma facility and find it's run by numpties. These are competent engineers that are running these facilities. But however, so often is the competency management is limited to the operations, the operators and technicians, and doesn't extend to the engineering and management. And so there's not that traceability. Again, that can be referred to. The LOPA can't say these people came and they were proven competent by whatever the company's name is, competency management system. So, this is something I'd like to see improved as time goes on. Okay, so again, I'm just picking which ones I'm going to go for. Safety functions of the SIF, fully defined and verified. So, whenever you read a LOPA and you read the comments, and you talk to the guys, they've usually gone through each independent protection layer with some detail. Will this protect us against this particular initiating cause? And they've usually done that quite well. But there's surprisingly quite a lot of times where the one thing they have never considered is the SIF itself. Does the SIF safety function do the job? Does it prevent the hazard scenario? Does it prevent the hazard scenario that you are actually studying? And I find it mainly when you've got where you're starting off with the safety function as like sort of in the title, and they've just accepted that. That's the safety function. It's got a written description already. It's all the LOPA sheet's already been prepared. We're now going to look at initiating causes. We're going to work out the frequencies. We're going to look at IPLs. And the team didn't say, actually, before we start, let's look and say, does that safety function actually prevent this hazard scenario? And it's probably the most important question to ask. Time at risk is another one where if I see time at risk, I would say there's more chance of being wrong than there is it's being right. Time at risk is rarely found to be justified. If you use time at risk, and you can have but when it's not at risk, if you can have an unrevealed failure of the initiating cause, that can occur at any time, you've got to be sure that that is not present before you go into the operating mode in which you are going to be at risk at. So in other words, you need to test and verify that these initiating causes aren't there before you move into that hazardous operating mode. But so often it's just discounted. We're only at risk when a tanker comes in. Therefore, this safety device, this initiating cause, it's only important 10% of the year that the ship's getting loaded. Well, that initiating cause may occur even when the ship isn't being loaded, and as soon as you start loading the ship, it immediately causes the hazardous event. So this is one of the areas that time at risk is so often fails at. Human failure there's a couple of things on human failure, credible human failure. The first one is whether it's initiating cause or an alarm response is getting the value, obviously getting justifying. I'm looking at is defining what it is the action is about. What's the action? And so often you'll see the initiating cause is your operator error, and that's as much as it says. But really, what you need to know is it's far more granular understanding. Therefore, you understand why they come up with the frequency, because it's usually what they're doing is related to the frequency. Valve in the wrong position following a shutdown. And then you can say, okay, how often do shutdowns take place? Take place once every 4 years. So you can start to get feeling where the frequencies comes from if they haven't written it down. Alarms are another thing where you've really got to define what your alarm response is. Now that's so rare. I've seen at best somebody will put credible credible operator response, and they'll say, "Oh, well, we discussed it." Yeah, and that's it. That's all you've got to go work on. The trouble is with an alarm and the human response is it can have such an impact on the time, in respect to time to respond, independence, and occupancy. If you see the alarm, do you have the time? What action do they have, and will they have the time to do it? What action do they need to take? Will they have the time to do it? Is what they're going to do going to be independent of other independent protection layers? Remember, the independence is key. So if they're going to go and start closing valves that were going to be closed by the SIF or by the control system, well, it's not really independent. And then, of course, is that alarm going to encourage that person to go out in the field to have a look, okay, or to deal with something? So you can no longer use occupancy. And often where alarms are used, if it doesn't have, if they have defined the alarm response, then you tend to use occupancy correctly. If they haven't, you tend to get this conflict where you also use occupancy, and then you challenge them and you say, "Oh yeah, I never thought that." Okay, the other similarly, the other thing is the probability values given to humans. Now, I will tend to look, if it's 0.1, I'm not going to question it. If somebody says, "Oh, human error is 0.1," it's such a conservative value, not going to question it. 0.01, I'm going to be looking for a little bit more justification. How can you claim 1 in 100 for a human error? If it's less than 0.1, I really want to see a study done. And I'm not the only one. COMA insists on it. I think it's, oh gosh, I'm trying to think of which COMA one it is. I think it's 12, the book on that, and it does ask for, for basically, well, it does say anything below 0.01 it needs to be justified. Okay, and we talked about credible independence between, we talked about independence several times now, and about how this is key. So, as I mentioned, behind the LOPA is a basic Bernoullian algebra, a simple fault tree that doesn't include a transparent means of compensating for the effects of common cause failure. Where you can deal with it in a fault if you're doing a normal fault tree, and therefore maintaining a credible independence is key to the LOPA. Despite this, a typical LOPA does not record evidence that the team considered whether sufficient independence has been achieved, given the overall risk safety requirements. Now, some will argue, okay, well, but surely that's the whole point of LOPA. We always say the independence, or they'll say we did discuss it. We don't need to, because it's so important. We don't need to mention it every time. And I'll forgive that. I'll say that's fine. But what I will say is, if you haven't documented about independence in your LOPA, then what I do want to see is another requirement of 61511 is common cause failure analysis. And that is what is a requirement. It's clause 9.4 for anyone who's interested. It's a requirement that so many people don't do. And yet it's not that hard, and this is a typical, for the vast majority of cases, a qualitative, check sheet process for evaluating independence is all you need. So just a systematic approach to say, has he got any? Is the impulse lines independent? Is this independent? Is that independent? Compared with the initiating cause and compared with the other IPLs, and identify those where there isn't independence, where there's common cause. And maybe provide a comment on that, and then eventually make an engineering judgment, saying yes, we still feel that there's sufficient independence. So there's nothing. Usually everything has an element of common cause when you burrow down deep enough. That's fine, so long as it's sufficient, and that's the key. And it's just demonstrating that. Okay, I've started all these because we're all instrument people, or I guess most of the people here are instruments, and therefore you're probably more interested in the instrument sort of areas. Generally, so maximum risk reduction claimed for BPCS is 10, or 0.1. Very rarely see that being abused in LOPA, But I do find errors commonly in fault trees. They don't mean to do it. It's just they've gotten a fault tree and they've gone, oh, the sensor or the failure rate, because they've broken it down into the separate components of the of the control system. Or the sensor, this will be this failure rate, and logic solver will be this failure rate, and the final element will be this failure rate. And then when you add them all up, it doesn't come to the 0.1. It's low. It's better, and you're not allowed to do that. Best you can achieve for BPCS is 0.1, no matter what method you use. And the HSC have backed this several times in, because that's been challenged by some companies. They said, oh, we've done a fault tree and we've done the analysis and so on. And the HSC have come back and said, no, it's 0.1.
Do you think that's too onerous though? Because if you think about these big DCS systems, with that sort of failure, with all the I/O they've got, they should be failing regularly and they don't. I agree with you. That I've been working with a company that's putting in a Honeywell safety manager and the Honeywell DCS, and the DCS is pretty much exactly the same in every aspect that you can imagine as the safety manager, but it's all the systematic management that's gone behind the scenes, isn't it? Everything's traceable in theory with the safety system, and that's why in theory you can claim better. But yeah, and I think it's sort of like they know that if they suddenly go, oh, we could be a bit flexible, it'd open the floodgates.
The 0.1's actually for the whole loop, though, isn't it? It's not just the DCS.
The what, sorry? The 0.1, yes, it's for the whole loop, yeah.
So that's one of the things you've got to be careful when you follow the safety. Think the control system, it's not the control system itself we're talking about.
Yeah.
It's not the sensor, you're talking about the valve.
Yeah.
It's that common cause as well.
Yeah, absolutely. There's another, actually, it's just out of interest. I've noticed that the American standards, they say, and obviously that comes to a lot in this country as well, because we tend to use the American standards. What they say is the 0.1 is for the whole of the BPCS. So if you got multiple, if you say you've got two BPCS independent layers, you can only claim 0.1 for the two of them. Or you know what I mean? Or I should say, you can't claim, can't claim 2 0.1s. You can only claim 0.1 once.
That's more like edition 1, isn't it? Really?
Yeah. So that hasn't changed much over there. So the another overlooked area of the standard is this thing of the limitation of risk reduction to instrument layers. So we're talking about multiple instrument layers to no more than 10,000 to a risk reduction factor no more than 10,000. Now, it's very rarely that I've seen that you do go over that 10,000, but it's not that hard. And as mentioned, if you get an alarm, as an IPL, and you have another BPCS layer, 0.1, say like an interlock, which is in your DCS, and then you include a SIL2 safe, that can take you over the 10,000 mark. Now, and then if you go over the 10,000 mark, then there's conditions, there's requirements. That's the point. But the point, what I often find is nobody tests it. Nobody tests to see if they've gone over the 10,000. They just put them in, and they don't do that. They don't do that test. They don't add them up and actually we've gone over our limit. And we should therefore we should stop, and we should start looking more deeply in qualitative risk, common cause failure analysis, that sort of thing. Quantitative, common cause failure analysis, which it asks for. So, it's just, as I say, I just don't see people testing that limit. And the other area, which rarely you see, but in fact it's just cropped up as I was doing this presentation, is the use of multiple SIFs credited. Okay, now you can credit two SIFs against one hazard scenario. That is allowed. It's not. However, it's often abused. Thankfully, rarely, and the long-term impact is never considered. So in theory, you could have a risk gap of 10,000, a risk reduction factor 10,000. So you're talking SIL 3, right on near borderline with SIL 4, and you can achieve that with two SIL 1s. Doesn't feel right, does it? But it's possible. However, you know, the SIL 1s each got a risk reduction of 100. However, if you start looking into a bit deeper, what you've got to start saying is this is where the common cause element starts to really hit. The level of independence needs to be extremely high here. And there's going to be, and particularly if the safety logic solver is common, because any common parts, they've not got to achieve the SIL 1, which you've just given a target for the SIF. They've got to achieve the SIL 3, near SIL 4. Their common cause. So, and this can get lost because you've just, I've got a SIF that says 100. I've got another one that says 100. And in the process of SRS developing, so these two, the relation between these two gets lost. But that relationship is there. And common areas have to achieve this higher SIL value. And that's not just the higher SIL value, it's also the higher systematic capability value. And then again, there's the opportunity, even if you did all that and did the studies, then there's the opportunity of getting lost in maintenance and operations and so on. So this is when I say it's the long-term part is very rarely considered. So basically, avoid this like the plague. It is really difficult to manage throughout the life cycle. It's an easy thing for the facilitator to say, oh, we'll put, why didn't you make that? You got SIF there, SIL 1. It's dead easy, looks on the paperwork, looks great. But it's a nightmare for the instrument people after that to manage. So, so that's I said, avoid that like the plague, basically. There is cases where, and I can give you, I'm sure they won't mind if I give you an example where it works perfectly fine. So all the North Sea comes through the Forties pipeline. The oil comes through the Forties pipeline, and there's a single SIF on the pipeline, and you can imagine that's a SIL because of it's one of the few SIL 4s that I've come across, and they have two SIL 2 systems in series protecting that. But what I will say is they've gone to the far end of they've really gone in depth to prevent prevent any common cause. They've got independent logic solvers, not just independent, but one's based on hardware, one's based on software. Everything is so independent, and not only that, but the way that they do the operations as well, and maintenance, and the testing. It's very much done on the principles of, or it was when I was involved, very much on principles of aircraft. You've got an aircraft with two engines. You have the way that they do maintenance. The same person was involved in one engine doesn't get involved in the other engine. So that's how I understand any road. I'm not involved in aircraft, but that's what I've been told. So that's the sort of principles that we did on the 40s. So conditional modifiers. time's getting on, so this is, luckily we're coming to the end. Conditional modifiers, as I called them before, look factors. There's certain conditional modifiers that I really don't like seeing, or I really ask questions about, challenge them, I should say. Things like hazard scenario developing and vulnerability. These are modifiers. So what they're saying is, well, we've got this initiating cause, but the chances of it actually developing and getting worse, the probability is quite low. The reason I don't like seeing that is because you've actually done that already. You did that in the HAZOP. You went, this is the initiating cause, this is the consequences, and you went, well, risk graph, we'll set a risk, and that risk is based on, well, how often does this sort of thing happen? Well, obviously, if it's something that doesn't happen very often, you'll have selected doesn't often happen in industry sort of column, So you've already taken that likelihood. It's already been taken. The likelihood of it happening has already been taken into account there. So if then you'd come along and say, oh well, it's not very likely to happen this, so we're going to put a conditional modifier in that says the chance of it developing is thing. There's a possibility there you double dipping. So I'm not saying there's not scenarios where you can use it. I'm just saying you've got to be careful with its use. And an FSA assessor would typically challenge anyone using them. Too many conditional modifiers. Well, there's so many different types of conditional modifiers, that I've come across. There's the usual ones. There's occupancy, there's a probability of ignition, but there's wind direction, and there's probability of a vapor cloud developing. There's vulnerability to people we've mentioned, and the list can go on. Is the person wearing the appropriate PPE I've put here? But I was just joking about that. But sometimes it can get a bit silly, and to the point where, and it's related to the next one, sometimes you can sort of mitigate the whole of your hazard, your problem, just through conditional modifiers. Basically, you say, oh, we don't need to put any protection layers in because, well, Lady Luck says, chances are it won't be a problem. I don't think that's the way to live our lives. I think we need to certainly as instrument people, we need to take control. And we would need to push for ensuring that there's proper independent protection layers, because they are the only layers that are going to prevent a hazard scenario. Occupancy, we've mentioned about the chances of an alarm leading someone into the area, but there's also something that's less used or less considered even than that, and that's when the events that lead up to a hazardous scenario, even before an alarm goes off, can often has influence factors that encourage an operator to go out there, or has influence, or happens because there's an operator out there, which is sometimes not always taken into account during when defining occupancy. So these are the questions. Is the reason this event is happening, is that because what are the events leading up to this sort of initiating cause, and are these events do these events lead an operator out in the field that now has increased the likelihood of the operator being out the field? So taking a standard 10% is not going to be sufficient, be the right amount. Oops. And there's one at the bottom I can't see because of this thing. I don't seem to be on. Don't know why. Can you see it? Oh, okay, yeah. I don't know what the last one will be. There's one, as I said, everything needs to be justified, and with regards to frequency, with regards to probability, with regards to probability with conditional modifiers as well. But conditional modifiers are particularly
vulnerable to, let's say, magic numbers. People go, oh, that happens about, the chances of that happening and somebody being in the area, 10%, it's very, very, they're more prone to having lack of evidence of, what they're based on. And it's more, seems to be more on gut feeling. So again, conditional modifiers are just a bit more vulnerable to that. Okay, so my final thoughts. So this is again a standard thing is to say is, look, we 6.5.11 and though it must admit LOPA is not really covered in detail in 6.5.11, but we've covered what we can, what is there. But it's been around now for 20 years and 6.5.8 even longer. And yet we continue on a learning journey. We're still all on a learning journey. And as we navigate this journey, be aware of the potholes and the fact that there are many well-trodden paths that lead in the wrong direction. Things based on, this is the way we've always done it. Okay. What I want, particularly the younger guys, is you need to challenge everything. You need to go back to the standard, read it, and say, "Is what we're doing, does it meet the requirements of the standard? Or is it something that we just got used to doing and we forgot to look at the standard?" Don't forget don't be afraid of making engineering judgments, so long as you are justified with traceable facts. Continue to, and I say that because particularly a common cause failure analysis as mentioned, which is just which I say was just a checklist. At the end of the day, you've got to make a judgment on that. You've got to say, I went through the systematic process, and I've got to make a judgment as whether the common cause is sufficient. The independence is sufficient. It's a judgment call on that one. And when I've given these sort of procedures out in templates, people go, "Yeah, but what's the calculation? Where's the calculation?" They love to have the numbers. Don't engineers love numbers? But sometimes it isn't the numbers. You've got to just have got to have the information, and so that you can make as a competent engineer, you can make the right decision. I always keep it in mind, open mind on everything, including this presentation. Analyse what you've heard, debate it amongst yourselves. Feel free to challenge me on anything, whether it be here or you can get me contact details. I haven't brought my cards, I don't think, but I'll have a look. But yeah, anytime, please feel free to contact me. And always remember to ensure that whenever you do a functional safety activity, that the results of it are credible, they're traceable, they're justified and documented. So thank you. Is there any questions?
What thoughts have you got on batch processes, and particularly with conditional modifiers, where people are saying, "Oh well, but in this batch process, that particular bit only occurs, and that hazard can only apply at that particular time." Have you come across that?
So, well, it's like this Tam mentioned earlier, but this where this basically say, we can reduce the frequency because of it's only, as you say, it's only hazardous for a period of time. That only works if the initiating causes can only occur during that period of time. If they can occur any time, then that fails the test. So, that's something worth consider. It needs to be considered. So that's what I'll be looking for. If anyone starts to apply that, it needs to be tested.
I'm
interested to hear you say at the very beginning that the target frequencies are not defined anywhere. Any company can define their own. In your experience, have you found companies defining vastly different ones, or are the acceptable frequencies for certain types of events fairly consistent from company to company to company?
Yeah. So usually a factor of 10 difference. Yeah. Some companies will have a it's also difficult which is high or low. Some will have a more demanding target than others. Those which have less, those you'll find that have a less demanding target will have more challenge more from the HSE is the first thing that'll happen. And they'll be expected to do a lot more work on proving their LARP than those that have a more better target, if you know what I mean. So this is what it's this balance, yeah, exactly. Sometimes what some companies do is, and I talked about those different risk targets, they'll purposely set their TMELs at a more demanding target, so they also meet this like individual risk scenario where you've got individual risks tend to be an issue where you've got a plant with a lot of risk, a lot of hazards. So you've got a lot of hazard scenarios within a confined place. So somebody could easily be, who's on that plant, could be prone to 10 at a time, 10 hazard scenarios at any one time. So immediately they've catered by setting their TMEL, so to be more demanding to cater with that situation.
Interesting. And do you find that companies take, let's say, environmental or reputational risks as seriously as what we'd see traditional sort of fatality type risks and fire and explosion risks? Do you think do people do these analyses for loss of credibility or damage to the reputation or damage to the pollution to the river?
Yeah. Well, yeah, again, you do see a lot of variety in that. So some companies will take environmental more serious than others. Usually you find them companies who've taken environmental conditions more seriously are those who've experienced scenarios that have actually happened and they've suffered financially because of them. And so because often you find, if you look from a financial point of view, you often find that environmental damage costs, tend to be higher than from fatalities.
Yeah, you kill one person, but
yeah,
pay them off in effect, and where's the millions of pounds worth of damage to the environment?
Exactly. So yes, but companies that haven't experienced that, they tend to be focused more safety and tend to have less focus on the environment, which is obviously something that I try to point out.
From industry to industry, that are the nuclear guys better than the chemical guys, or are the pharmaceutical guys better than the petrochem? Or?
Oh, I think I don't think so much. It's the sectors as such. It's more the individual companies. What I will say is, the bigger the company, you would expect the bigger the company to be better at this. They've got more resources, they've got more people, they've got more expertise. I actually find the opposite. I actually find it's the smaller companies who haven't got the size to challenge the HSE. They tend to say, right, okay, this HSE have said this, I've got to find a solution. If you're in a big company and they say, the HSE go there, they'll say, how do we challenge that? We'll push back on the HSE. That is often the case, it's that will happen. So it's so I've actually, I would say I've learned so much since leaving BP, which is about, I spent 20 years on, and from these smaller companies in the regards of how they've solved issues that I've known have existed in BP and we never did have a solution for. And these smaller companies have solved them. They found practical ways of dealing with it.
Thanks, Ian. What's your thought on taking? I've seen recently a pressure trip, and they reduced the sill level on the pressure trip through the LOPA by taking advantages of diverse technology, but they were all essentially relief valves. So they were looking at like a relief valve, bursting disc, a buckling pin valve, all kinds of relief valves, but because they were independent technologies, they were just piling up the point ones. It felt wrong to me. That.
Right, okay, yeah.
What's your thoughts on that?
Well, again, it's, see, I never, if I came across that sort of scenario, my first challenge would be, okay, have you done some sort of common cause analysis on that? You know, have you looked at, is there anything that if the process was prone to blocking, you know, prone to plugging, sorry, you know, would all these three methods be therefore prone to that? It might, you know, or some, you know, would some of them be prone to that? And it's only, so I would only mainly be challenging them on, let's show the evidence. The way I see, you can.
You would accept it if they.
I would accept what.
A clean service or something like that.
Yeah.
Would accept.
I would accept if they can provide justification with you know good evidence.
Please you said that. Got put in.
Well, the point of the law, isn't it? A lot of people miss that actually that is your option here in
Yeah.
study. That's what it's about.
Yeah.
Looking for the best solution.
Absolutely.
So one of the challenges I get, quite frequently when you're going through the law, is that this will never happen. Scenario, so people are looking at it and looking at the LOPA, believing it's kind of forecasting when a hazard's going to happen,
Yes.
rather than realising that what the LOPA is actually about is completely the opposite. It's about trying to show a regulator that the hazard is not going to happen and why.
Exactly.
You've seen a lot in your experience as well?
Well, yes. So that, I mean, specifically in the early days, I mean, what I've come across is, it's, you know, when we deal with these targets, these TMEL targets, particularly for the higher severities, and we're looking at 1 in 10,000 years, 1 in 100,000 years, you know, and even more demanding than that. People can't get their heads around that. Do you know what I mean? So particularly when they've been on a plant for 20 years, we've never had any problems. But when you're looking at, they're only looking at 20 years, which is such a small time compared with their target of 10,000 years, 100,000 years. And so you've just got to try and say, look, it's, you know, we've got to go with the maths because this thing is it's just incomprehensible. And we cannot deal with it in our sort of lifetime, because what we need to be thinking of is, it's not just your plant that's doing this. There's 100 of these plants around the world. So it's 100 straight away. It's 100 times. So every year we've got 100 years of it. You know, it's going to happen. You know, potentially on one of them. 100 times more likely, sort of thing. So it's yeah. So it is this difficulty of, it's just it's a human thing. You know, it's being able to marry something that's so small with human ability of human's own experience.
I'm interested in your comments that the process engineers have now taken all this over and the instrument engineers have been sidelined. Because when this first came out, it was totally the opposite way around.
Was, yeah. Yeah.
It was a struggle sometimes to get the chemical engineers involved.
Yeah.
Except when they wanted to do a full QRA.
Yeah, yeah. No, that's right. And to the fact, I would say it was actually swinging the other way now, because I'm finding so many times I go to a site and I look at the LOPAs, and you find it's just all process engineers and they've been involved, and no instrument person available. It's
one of the fundamentals of ASOP and LOPA was that it was a team event.
A team, yeah.
Skills, the total skills.
Absolutely.
That were necessary.
Yeah, and that's the problem when it comes to, like, particularly when you can look at the probability of the failures and this, talking about independence. If you haven't got that diverse team, straight away the independence part, which tends to get lost, because it's the instrument person that knows, that part more than anyone else. So yeah, it does fall. it is a worrying trend going in the opposite direction at the moment. Yeah. Okay, I think that's it.
Thank you very much. That was excellent.
Thank you.